Hi, and welcome to Allen High School's discussion of chemistry at the 10th grade pre-AP or honors level. We are finishing up our conversation on bonding and properties that go along with that bonding. We've talked a lot about covalent molecules and the structure of covalent molecules, and you did an activity in class in which we looked at the polarity of molecules. And a polarity is about a pull on electron density. Now, you can have a polar bond in a molecule, but still have a molecule that is nonpolar. All right, so there's a difference between bond polarity. For example, if I have a bond between carbon and oxygen, that is a polar bond. Oxygen's more electronegative, so it will draw electrons towards it and be partially negative, leaving the carbon partially positive. That is a polar bond. Now, let's take a look at the entire molecule. This would show the whole CO2 molecule, in which you have two polar bonds. So that's a polar bond, that's a polar bond. But because we have an even pull on both directions, means, remember from class, we've done this in our little activity, even pull on electron density is going to be non-polar. And that's very important in terms of its properties. So that's a non-polar molecule. So make sure you see that distinction carefully between a bond and the molecule. So in non-polar molecules, the central atom, and this is key, has no non-bonded pairs. In other words, when you're doing your ABX formula that we taught you, there's no X. All right? And it's surrounded by the same atoms. There's no preference of electron density on one part of the molecule. It's symmetrical around the central atom, and we call it a non-polar molecule. Now, this is quite important. The attraction between two non-polar molecules. So if I could draw this again, this Cl and Cl, I tried to cut and paste it and it wouldn't work in the format I'm using right now. If we wanted to take a look at the forces of attraction between these, we're going to give it a name pretty soon, but this attractive force is very weak. And so it doesn't take much energy to break it. It takes energy to break, takes to break. Freeze to form, takes to break. What that translates into in terms of property that you need to know for your test are these have very low melting points and low boiling points. They are typically liquids or gases at room temperature, although if nonpolars get really big, let's think butter. So if they get really big like butter or some fats, then they can be solids at room temperature. But they're going to be typically not solids. They do not, covalence period, doesn't matter whether they're polar or nonpolar, covalent molecules do not conduct electricity in any way, shape, or form. There's no pathway for mobile electrons. There's no charges for them to hop through. There's no freedom for electron motion. Nonpolar are insoluble in water and other polar solvents, but they're soluble in nonpolar solvents. So what you can think of is that water is kind of your penultimate example of a polar, whoops, my Mimio's getting low on batteries, it's jumping on us, sorry. A polar solvent. And oil, right? Oil and water don't mix, right? Oil is a non-polar solvent. Well, like dissolves like. You want to write this down someplace. Like dissolves like. Polar in polar, nonpolar in nonpolar. Okay? So, nonpolar would be soluble in oil or gasoline. Okay? Now, for polar molecules, the central atom has either an X at your level, and I got around to a few tables to tell you this. In these ABX formula, at the pre-AP level, if you see that non-bonded pair, remember X stands for the non... my Mimio's going crazy. I'm so sorry. The electrical in it is going nutso. Okay, non-polar. Okay, excuse me, non-bonded pair. Non-bonded pair of electrons. I don't know what's happening with my Mimio. I'm so sorry. Non-bonded. That extra pair of electrons. If you see that, it's automatically a polar molecule. That's not true at the AP level, but it is true at the pre-AP level. All right? So if it either has an X associated with it, or we have different atoms, here we have a hydrogen and 3 chlorines, it's not the same. It's not symmetric. It's unsymmetric. That's going to give us a polar molecule. Now, the attraction between two polar molecules is typically stronger. So they tend to have higher melting points and boiling points. And that's assuming we're comparing the same size. Okay? So if we're comparing substances that are similar size, then the polar is going to have higher melting points and boiling points. Most are now liquids, such as water or ammonia at room temperature. It doesn't matter what kind of covalent it is. It won't conduct electricity. They are typically soluble in water, and it exists as a discrete molecule when it dissolves. It doesn't separate into ions when it dissolves in water. So what you want to look at is the distribution around the central atom. If it's the same all around the central atom, if the answer to that is yes, it is the same, then it's non-polar molecule. If it's no, that means there is an uneven pull on electrons, and it is a polar molecule. Okay, so that's kind of a summary statement, even though I can't write. Okay. Now, 3 sides have one element and the fourth is different. It's polar. So all 4 sides are the same. It's nonpolar. 3 the same, 1 different. 2 the same, 1 different. It's polar. Okay, so I think that gives you some good idea. I'm going to forgo this example. I'm just going to give you the answer. This happens to be a non-polar molecule, and non-polar molecules would dissolve in non-polar solvents. So that's a non-polar solvent. So it would be more likely to dissolve in oil than it would water. All right? Okay, I'm going to skip this part for now because we've done a lot of it, and until our next video when we'll pick up with metallic bonding, which is quite short. This is signing off.